Hello, I'm the Magnate Mr. Daycock, and today I'm going to be teaching you about finding complex roots of numbers. Now this isn't too difficult a task, but it does require a bit of thought involved. So, first of all, we want to solve the equation z cubed minus 1 equals 0. Now, this might seem very easy. All you need to do is write it as z cubed equals 1. Now this might seem very easy. All you have to do is write it as z cubed. It's going well. Now this might seem very easy. All you have to do is write it as z cubed equals 1, and then we take our cube root, so z is equal to the cube root of 1, and of course that's just 1. And we're done. Except we're not, because this is a cubic equation. And so we expect it to have 3 roots. So where did the other roots go? Well, we lost them when we took the cube root. Because let's imagine, if we think about it and we had equation x squared equals 1, that means x is equal to plus or minus 1, not just 1. When we take a square root, we have to consider a second solution. The same applies here. Whenever we take a cube root, we need to consider there's 3 solutions. Or if we have to take a 5th root, there might be 5 solutions, and we need to consider that. And the question is, how do we take account of that? How do we deal with this situation? Well, what we do is we remember our Argand diagram. And 1 is, of course, here. That's the number 1. And we remember that we can write any number in an exponential form. We can write any complex number as z equal to r e to the I theta. In this case, where r is of course the magnitude and theta is the argument. In this case, when we're dealing with 1, r equals 1 and theta equals 0. So we can write this as, when we're dealing with 1, we can write 1 as equal to 1 times by e to the I times 0. Which shouldn't be a surprise because that's e to the 0, which is of course 1. But that isn't the trick. The trick here is to notice that's not the only way of writing 1. On this Argand diagram, we could take a full turn first. So we could write 1 as equal to e to the 2 pi I. Because it's a full turn, our angle is theta equals 2 pi. So e to the I theta becomes e to the 2 pi I. So we could also write 1 like that. Or we could write 1, we could take a third turn. We could write 1 as equal to e to the 4 pi I. And that is the trick. The thing we want to take the root of, rather than just writing its principal angle, we need to consider all the possible angles it could take. So we're going to write 1 as being equal to e to the 0 I, certainly, because 0 is our principal angle, 0 plus 2 pi n I. And in this case, that just means it's e to the 2 pi n I, and of course n needs to be an integer. It doesn't have to be a positive integer, it could be a negative one, and often the easiest ones to pick are the ones around 0, so for a cube root we'd pick 0, 1 and negative 1. But it could be actually any integers whatsoever. In fact, it could be any consecutive integers. You could pick a 100, 101, and 102, and you would still work. You would still get your 3 distinct roots. But we want to go with the easiest options. So in this case, we're going to rewrite 1 as this. And now we're solving the equation z cubed is equal to e to the 2 pi ni. And therefore z, taking a cube root, but remember a cube root is actually a power of a third, so we're going to take the third root, the third power of these, and we get e to the 2 pi ni, the power of a third, and we get z is equal to e to the 2/3 pi ni. And then all we need to do is plug in our possible values of n, which, as I said, we can put n equal to -1, 0, and 1, and we get z equals e to the -2/3 pi I, z equals e to the 0, and z equals e to the +2/3 pi I. And of course, our middle one is just 1. But what about our top one? Well, our top one has an argument of z equal to -2/3 of pi. And therefore, it can be written in the form z equal to cosine of -2/3 pi plus I sine of -2/3 pi. And that's really important. Equally for the one on the third one, we get z is equal to cosine of 2/3 pi plus I sine of 2/3 pi. And these aren't too difficult to work out. You can do them whatever way you feel is appropriate, but obviously just stick them in a calculator and you can pretty much get your answer. And what you'll get here is you'll get z. Or in fact, often you can just leave it this way. Often they'll accept that as an appropriate answer. But if you want to calculate this as an answer, cosine of -2/3 pi is equal to 1/2, and sine of -2/3 pi is minus √3/2 times I. So our 3 roots are z equals 1/2 minus √3/2i, z equals 1, and z equals 1/2 plus √3/2i. And there you go. There you have it. These are our 3 solutions. These are the 3 roots of 1. The 3 cube roots of 1. And you can test it out. You can cube these and see that they will in fact give you 1 every time. It might seem a little bit surprising that that will give you 1 and that will give you 1, but they absolutely do if you cube them. And there's a very nice property here. Ooh. Apologies there, I made a bit of a mistake. Cosine of -2/3 pi is -1/2 and -1/2. So these are our 3 roots, and like I was saying, they have quite a nice property where if you add all 3 of them together and sum them up, the real parts, -1/2 plus 1 plus -1/2 is 0, and -√3/2 plus 0 plus √3/2 is also 0. So if you add together these roots, you get 0. Now this is only guaranteed to work if you're dealing with the cube root with the roots of 1, but it will work with any roots of 1. And in fact, this root squared is this root, and vice versa. If you square one of these roots, you in fact get the other one. And again, that iterative process of powers applies to any roots of 1. We will actually call those the roots of unity, unit being a term for 1. And one last thing to note is we can draw this on an Argand diagram. And the 3 roots are, of course, are 1, our negative a half plus root 3 over 2, which is here. Yeah, about there. And there. So we get our 3 roots here, and these actually will form an equilateral triangle with its centre at the origin. So that's also very, very nice. And again, if you did the 4th roots, you'd get a square. If you did the 5th roots, you'd get a pentagon, and they'd all be equilateral. So that's very nice. Now let's go up to here, and this question hasn't come out quite right. So let me change that, because that's the same again. We're going to solve z to the power of 7 plus 3 minus 3i equals 0. Now, to solve this, I'm going to rearrange it. We get z to the power of 7 is equal to negative 3 plus 3i. And we can put that on an Argand diagram. So whereas negative 3 is here, plus 3i is here, and we're going to have our point there. So the point we care about is this point in our plane. And we want to find the 7th root of that. So what are we going to do? Well, first of all, we need to write it. We need to write this number on the right in our r e to the I theta form. So we need to know r. Well, the r, the modulus of this, is equal to the square root of 3 squared plus 3 squared, which is equal to 3 root 2. So our modulus, our r, is 3 root 2. And our theta is going to be equal to the arctan of 3 over negative 3. But remember, there are 2 solutions to that. And we need to look at this and notice that it is our positive solution we're looking for. So our answer is 3 over 4 pi. So as opposed to negative a quarter pi, which is what you'll get if you don't consider which is the correct solution. So we can write this number as, we can write this equation now as z to the 7 equal to e, let's not forget the r, so 3 root 2, or perhaps we'll even write that as, put that as 18 to the power of a half, because that's ultimately what we get. 18 to the power of half multiplied by e to the I theta, so 3/4 pi I. And that's one root. That will give us one root, because we can just take the 7th power on each side, take it to the power of a 7th. But here, we need to consider all the other possibilities. So we also need to say plus 2 pi ni on the end. And that will give us all our multiple solutions. Okay, now let's take that. So now we have that, let's take our 7th root. So we get z will be equal to, taking the 7th root, 18 to the power of 1/14 multiplied by e to the 3 over 28, and I'm factorizing out the I just to make it easier to deal with, plus 2/7 of pi I. And very, very importantly, don't forget the n there. And now, this is our answer. We just need to put in 7 consecutive values of n. And again, recommended would be -3, -2, -1, 0, 1, 2, and 3. 7 consecutive values of n in order to get our 7 different roots, and our 7 different roots will be z equals, and in this case I am just going to leave it in sine cosine form, and in fact I'm not even going to work out what the 14th root of 18 is. The 14th root of 18 multiplied by cosine of, and putting in -3, and get -21 over 28 pi plus I sine of -21 over 28 pi. For n equals -2, we're going to get the 14th root of 18 multiplied by cosine of -13 over 28 pi plus I sine of -13 over 28 pi, and then so on and so forth. We're going to get cosine of -5 over 28 pi plus I sine of -5 over 28 pi. Plugging in 0, we're going to get z equals 14th root of 18 multiplied by cosine of 3 over 28 pi plus I sine of 3 over 28 pi. Z equals 14th root of 18 multiplied by cosine of 11 over 28 pi plus I sine of 11 over 28 pi. And you might be able to spot a pattern at this point. Z equals the square root of 18 multiplied by cosine of 19 over 28 pi plus I sine of 19 over 28 pi. And lastly, we get z equals the 14th root of 18 multiplied by cosine of 27 over 28 pi plus I sine of 27 over 28 pi. And interestingly, if you carried on from there, you would just get roots repeating over and over. If I carried on, I would get that original root again. Okay, and there you go. There are the 7 different solutions, and you could work these out as a decimal by putting it in your calculator. But we get the 7 different solutions to our equation up here, which was z to the 7 plus 3 minus 3i equal to 0. Okay. Thank you very much for watching, and I'll see you in the next video.